right, let's start. Welcome back. So just a quick announcement. So the lectures and also lecture notes of the previous talks, you can find them online on the homepage. Redirecting to some YouTube channel and everything is there. So in case you miss something, you can just look it up. And now, without further ado, Jacob, with this third lecture. Thank you.
All right, thank you. So I followed a link to the first lecture on YouTube, and I realized that not only did I end the previous lecture 15 minutes early, I also ended the first lecture 15 minutes early. So I want to make sure that you get your money's worth for flying me out here. I think this time I've prepared way too much material and that I won't get through it, but we'll see. All right, so let me begin with a brief recap of last time. So last time the setting was we had an FP algebra R, X was its spectrum, and I described to you a construction that took p-torsion étale sheaves on X and out of them made Frobenius modules over R, and that was some fully faithful embedding. I'm denoting it by RH because I'm thinking of it as something which solves a characteristic P version of the Riemann-Hilbert problem from the first lecture. And so let me just very briefly review a couple of properties that this construction has. So first, if you apply this construction to the constant sheaf, what you produce is the perfection of the ring R, the ring that you get by taking R and adjoining all P power roots of its elements. It's an exact functor between abelian categories, and it's compatible with direct images, not in general, but along finite morphisms. And in particular, it's compatible with direct images along closed immersions. Now, something that I alluded to last time, but I didn't really explain, is that essentially this construction is determined by these properties. Maybe not in a strict mathematical sense, but morally, you can, knowing that you want to have a construction with these properties, you can kind of figure out what it is you have to do. So let me spell that out a little more explicitly. So first, a convention for this lecture and all the remaining lectures. Whenever I say something is a scheme, I mean that it's a scheme which is quasi-compact and separated. So if you're interested in the category of p-torsion étale sheaves on X, it has generators. It's generated by the sheaves which are represented by schemes which are étale over X. So for every U which is étale over X, you can build a sheaf by taking the constant sheaf on U and extending by 0 to X. And those sheaves generate the category. So if you want to understand the Riemann-Hilbert functor, you really want to understand what it's doing on those generators. Now, this is pretty easy to say if U is finite étale over X. In that case, this sheaf is a local system. In general, it might not be finite, but you can always compactify it. You can embed U into as an open subset of some scheme U bar, where U bar is finite over X. And in that case, U bar is an affine scheme. You can write it as the spectrum of some R algebra S. And the boundary of U bar is going to be the vanishing locus of some ideal that I'll denote by J. So in this situation, the constant sheaf on U bar has a decomposition. It has a subsheaf, which is supported on the open set U, and a quotient sheaf, which is the constant sheaf supported on the boundary. And the Riemann-Hilbert functor is exact. So I'm going to take the Riemann-Hilbert functor for S now and apply it to this exact sequence. And I should get an exact sequence of Frobenius modules over S. And now what each one of the Frobenius modules, we can say what it is. Well, because the Riemann-Hilbert functor is compatible with finite direct images, the term on the left, that's the thing that we're trying to compute. That's the Riemann-Hilbert functor for R applied to this generator associated to the étale U. The thing in the middle, that's the Riemann-Hilbert functor for S applied to the constant sheaf, so it gives the perfection of S. And the thing on the right, by the same argument, gives the perfection, well, not of S now, but of coordinate ring of the boundary, which is S mod J. And so from this, you can read off what you wanted, the Riemann-Hilbert functor applied to this generator. It's what you might call the perfection of the ideal J. It's an ideal in the perfection of S, which is generated by elements of J and all their p power roots. Okay, so I'm going through this because this is what I want to generalize in this lecture. I want to now do something like this, but where we're not working in characteristic P. So as I mentioned in the last lecture, the theory of P torsion sheaves on FP schemes, it's kind of a toy theory. It's not very interesting. I would like to make things more interesting in this lecture and the next by extending the definition of this Riemann-Hilbert functor to situations where the coordinate ring R is not P torsion, but it's maybe still P complete. And at the same time, we're going to extend the definition to the case where the sheaf F is also not assumed to be P torsion. Okay, so I should mention everything that I describe in this lecture is joint work with Bhargav Bhatt, and that's true for all of these lectures that I've given. If I'm ever describing something that I've played a role in, it was with Bhargav Bhatt. Okay, so what's the obstacle? On the previous slide, I kind of gave you a formula for the Riemann-Hilbert functor, at least what it should do on generators. Why don't you just take the same formula? And the problem is that the formula involved this notion of perfection. And that's a sort of characteristic P idea. So what should replace it? So let's just review the notion of perfection in characteristic P first. So let R be an FP algebra. Then this ring that I've been denoting by R 1 over P to the infinity, one definition of it is that it's a direct limit of a sequence of rings where each of those rings is equal to R, and each of the transition maps is the Frobenius map. It's the map that sends each element to its pth power. So that's what you might call a construction of the perfection. But you could also define the perfection by a universal mapping property. It's the universal example of a perfect R algebra. So what that means is that first of all, it's perfect, meaning every element has a unique pth root. And second of all, any homomorphism from R into a perfect ring factors uniquely through this perfection. So if you know what you mean by a perfect ring, then you should know what you mean by perfection. So that's a characteristic P idea, but recently a very useful generalization of the notion of perfect ring was introduced by Peter Schulze, this notion of a perfectoid ring. So let me review this notion of perfectoid ring there's a lot of ways to give the definition, but I'll pick one that's going to be convenient for what we're going to do with it. A commutative ring R is perfectoid if it has a presentation of a very specific form. You can write it as a quotient ring A mod I, where A is something that looks like the Witt vectors of a perfect FP algebra S. I is a principal ideal in A. So it's an ideal which is generated by a single Witt vector. And every Witt vector you can write as a Teichmuller representative plus P times something else. And you demand first that this element pi that you're taking the Teichmuller representative of, that S is complete with respect to pi. And secondly, that this element U that appears as the coefficient of P is a unit. So how are you supposed to think about this? When you demand that S is p-adically complete, that's in some sense saying pi is very small. And so you're taking this ring W of S and modding out by something that is almost a unit multiple of P. And so the quotient ring should in some sense almost look like you divide it out by P, which would give the perfect FP algebra S. So in some sense, this definition is trying to say that R is a lot like S. On the other hand, R might look quite different from S. For example, S is assumed to be an FP algebra, R might be a ring that has no p torsion at all. So just a bit of terminology. In the situation of this definition, this pair A comma I is an example of a perfect prism. And the definition I've given here is that A is perfectoid if it has a presentation of this form. But if that presentation exists, it's essentially unique. Everything in here, except for the choice of generator of the ideal I, is actually uniquely determined. So a more precise statement is that the category of perfectoid rings is equivalent to the category of perfectoid perfect prisms, the category of data like this. And in particular, if I give you R as an abstract ring, you can recover that perfect FP algebra S. It's typically denoted by R flat. And concretely, you can construct it as the inverse limit of a sequence of rings, where each of those rings is R mod P, and each of the transition maps is the Frobenius. Okay, so this is a definition of a class of rings, and you can think of them as a mixed characteristic replacement for the notion of a perfect ring of characteristic P. So let's try to take this and use it to define some notion of perfection when you're not in characteristic P. So let R be a commutative ring. Definition, a perfectoidization of R is an R algebra, which I'll denote by R puffed, with two properties. First of all, it should be a perfectoid ring. And second of all, every homomorphism from R to a perfectoid ring should factor uniquely through R puffed. So just an example, suppose that R is an FP algebra. Then R is perfect if and only if it's perfectoid. And that's true not only for R, but also for any R algebra. And therefore, the perfection of R in the usual sense is also a perfectoidization of R in the sense of this definition. Okay, so that's a definition, and it's by a universal property. So if a commutative ring R has a perfectoidization, then it's uniquely determined up to isomorphism. But warning, these usually don't exist. So for example, a perfectoidization of the ring of integers or the ring of p-adic integers would be an initial object in the category of perfectoid rings. And the category of perfectoid rings does not have an initial object. But this is actually good, not bad. So if you, previous lecture where we were talking about the characteristic P story, I started by saying, let R be an FP algebra. And then we did a bunch of things with it. But for more or less everything I said, there would have been no harm in replacing R by its perfection. Replacing R by its perfection doesn't change the category of étale sheaves. It doesn't change the category of perfect Frobenius modules. Doesn't change the constructions that I was describing. But in mixed characteristic, that maneuver of just taking any ring and making it perfect is not available because of this. And that's going to be responsible for a sort of big gap between the story that I'm telling you in this lecture, which is about a perfectoid ring, and the story that I'm going to tell you about in the next lecture, which is going to be about more general rings. And that's going to sort of enable the eventual story to be a lot more interesting than the characteristic P story that we told last time. Okay, so these perfectoidizations, they don't always exist, but sometimes they do. So let's suppose that R is a perfectoid ring. It's presented as A mod I. The theorem of Bott and Schulze is that every finite R algebra admits a perfectoidization. Finite means that it's finitely generated as a module over R. And not only did they prove that it exists, they gave a formula for it. They gave you a way of constructing it using their theory of perfected prismatic cohomology. So if S is finite over R, what they proved is that if you take the perfected prismatic cohomology of spec S, or spoof S if you prefer, then this is actually lives only in degree 0. It's just some commutative ring. And moreover, if you take that commutative ring and together with the ideal generated by I, that's a perfect prism. And so if you reduce that commutative ring modulo I, you get a perfectoid ring. And they showed that perfectoid ring has the universal property. It's the universal example of an S algebra, which is perfectoid. Okay, so I want to make use of this. I want to define some notion of perfectoidization with compact supports. So for most of this lecture, R is going to be a perfectoid ring, X is going to be its spectrum. And now let's suppose that I give you a scheme which is étale over X. So as before, it might not be finite étale, but I can compactify it. I can embed U as an open subscheme of some U bar, which is finite over X. So then U bar is the spectrum of a finite R algebra S. And the boundary of U bar is cut out by some ideal that I'm again going to denote by J. And in this situation, both S and S mod J are the kind of algebras to which the preceding slide applies. They're finitely generated as R modules, so they admit perfectoidizations. And the perfectoidization of S maps surjectively onto the perfectoidization of S mod J. And I want to take the kernel of that surjection. So that's some ideal in the perfectoid ring S puft. I'm going to denote it by gamma bar C of U. So the C is to make you think of compactly supported. I want to think this is some notion of the perfectoidization of U with compact supports. So this is an ideal in S puft. In particular, it's an R module. And something that's not obvious from this construction is that it's independent of the choice that I made. It depends only on U and not on the way that I've chosen to compactify it. Okay, so why am I giving you this construction? It's because it recovers what we did in the second slide, right? If you're in the situation where R is a perfect FP algebra, that's an example of a perfectoid ring, and let U be étale over the spectrum of R, well then this perfectoidization with compact supports that I just defined is what you get by taking the Riemann-Hilbert functor and evaluating it on the constant sheaf extended by 0 from U. That's exactly what that calculation on the second slide was showing. In particular, this would be a Frobenius module over R, but that's a fluke. That's not something that you should expect in the more general situation, because it wouldn't even make sense in the more general situation. A perfectoid ring R, when it's not of characteristic P, doesn't have a Frobenius, so it doesn't make sense to talk about a Frobenius module over R. But nevertheless, the Frobenius is going to be an important part of the story. So let me do a slightly fancier version of this construction. So same setup, let R be a perfectoid ring, let X be its spectrum, and let's say we have an étale R scheme U. And we can choose a compactification of it, embedded in something that's finite over R. And now in this situation, you can look at the perfected prismatic cohomology of U bar and the perfected prismatic cohomology of the boundary. And those are both concentrated in degree 0 by that result that I mentioned earlier. There's a surjection between them, and the kernel is some ideal that I'm going to denote by gamma C of U without the bar. So this is perfected prismatic cohomology with compact supports. So this is an A module, and again, it's not clear from the construction, but one can show that it's canonically independent of the compactification that you choose. And it's related to the preceding construction. So this gamma C without the bar is an A module, but when you reduce it modulo the ideal I, you get gamma bar C, which is an R module. Okay, so this is a construction that you can do for anything étale over X, and I want to turn this construction into a functor. All right, so notation, anytime you have something étale over X, I'm going to write HU for the abelian sheaf, which is represented by U. So now I'm going to take the constant sheaf with value Z on U and extend it by 0 to X. So those are generators for the abelian category of abelian sheaves on X. And now I claim that there's an exact functor, which I'm going to denote by RH prism. It goes from the category of constructible sheaves on X to the category of perfect Frobenius modules over A. And the defining property of this construction is that it takes each one of these generators, HU, to this prismatic cohomology with compact supports that I defined on the previous slide. So I'll call this the Riemann-Hilbert Functor associated to the scheme X. Maybe one remark is that this might look a little weird to you. Maybe you talk about, it's maybe a little bit strange to talk about X with sheaves on X where the coefficient ring is not finite. So if you prefer, you could replace the category of abelian sheaves with p-adic étale sheaves, and you would have the same statement. So I'm not going to prove this proposition to you, but I want to just give you a sense of the kind of thing that it's saying and the kind of thing that goes into the proof. So let me do an example. So let's start by taking an open subscheme of X whose complement is defined by some ideal that I'll denote by J. So what does gamma bar do in this situation? So U, I can compactify by embedding it into X, and therefore this prismatization with compact supports, I would take the kernel of the map from the perfectoidization of R, which is just R itself, to the perfectoidization of R mod J. So that's an ideal inside of R, which I'll denote by J puft. It's the perfectoidization of the ideal J. It's an ideal that you get by taking J and enlarging it as much as you need to guarantee that the quotient ring is a perfectoid ring again. So that's what this gamma C does to U. And now let's suppose that I give you a Galois covering of U with the Galois group, some finite group G. So then I can choose a G equivariant compactification. Let me denote it by V bar, write that as spec S. And you can see what gamma bar of V is supposed to be. It's obtained by more or less the same construction, except rather than getting an ideal inside of R, you get an ideal inside of S puft. Now in this situation, this group G is acting on the abelian sheaf HV, and the fixed points for that action is the abelian sheaf represented by U. In fact, you can be a little more precise. The sheaf HU has an acyclic resolution given by the cochain complex of G acting on HV. Now, if you believe what I said on the previous slide, that there's this exact functor from the category of constructible abelian sheaves satisfying some properties, then you should be able to apply it to this acyclic resolution and get some resolution in the world of Frobenius modules. So if you take that and you reduce it modulo the ideal I, you learn something, which is that if you take the cohomology of the group G acting on this ideal JS puft, that looks like J puft in degree 0 and vanishes in all other degrees. So if J is the ideal generated by P, this is the setting of the almost purity theorem of Peter-Schulze. And this is one of the consequences of the almost purity. This is one of the parts of that statement. And when J is an arbitrary ideal, this is, again, a part of a generalization of the almost purity theorem due to Bott and Schulze. So you should think of the existence of the Riemann-Hilbert functor of the previous slide as something like the almost purity theorem. It's, there's a big overlap in what you have to check and how you check it. Okay, so that was a construction in the world of abelian categories. I would now like to extend it to derived categories. So let me just make a remark. This RH prism, for every constructible sheaf F, it assigns an A module, and that A module is automatically complete, both with respect to P and with respect to the ideal I. And when we pass to the world of homological algebra, we want to retain those properties. So I'm going to write dA for the derived category of A, and inside it, there's the subcategory, which I'll denote by d hat of A. That consists of complexes which are both p-adically complete and i-adically complete. And then this functor that I described earlier can be promoted to a functor of derived categories. I'll denote it the same way. RH prism, it goes from the derived category of abelian sheaves on X to this category d hat A. And just, I'll call this again the Riemann-Hilbert functor. And a warning, one of the reasons that I want to pass to derived categories is that this functor is not quite t-exact. So the functor I described earlier was on the category of constructible sheaves. So those go to complexes of A modules with cohomology only in degree 0. But a non-constructible sheaf, even if it's in degree 0, in general goes to a complex with cohomologies in many degrees. Well, not very many degrees. It's almost t-exact. The problem is that the construction here involves some kind of completion with respect to P and I, and completion is not an exact functor. Okay, so let me tell you a little bit about how this Riemann-Hilbert functor works. So R is a perfectoid ring, X is its spectrum. So first, it takes the constant sheaf on X to the ring A. It carries tensor products of sheaves to tensor products relative to A with two caveats. First of all, we're working at the derived level, so all these tensor products are derived. And second of all, we're thinking only about pi complete A modules, so that tensor product has to be completed. This Riemann-Hilbert functor produces not just A modules, but Frobenius modules over A. That is, RH is always equipped with an automorphism, which is semilinear with respect to the Frobenius on A. This functor automatically annihilates any sheaf on which P acts invertibly. And as a consequence, it factors through the operation of p-adic completion. So if you think it's a little funny to talk about the derived category of abelian sheaves, again, you could replace it by something like p-adic étale sheaves, and you wouldn't lose any information. And finally, something that is going to be very important in the next lecture is that this construction is compatible with base change. So if you have a map from R to another perfectoid ring S, and you have some sheaf on spec R, you can pull it back to spec S and apply the Riemann-Hilbert functor there. Or you could apply the Riemann-Hilbert functor on spec R, and the resulting modules, one is just obtained from the other by extending scalars. Okay, so I'm calling this the Riemann-Hilbert functor, but it doesn't quite fit into the paradigm that I set in the first lecture, where I said a Riemann-Hilbert functor is something that takes topological data, something like étale sheaves, to quasi-coherent data, something like modules over whatever the coordinate ring is. So this is a construction where you input étale sheaves and it outputs modules over A rather than R. But you can fix that. So I'm going to write RH prism bar of F to just mean what you get by taking RH prism of F and reducing it modulo the ideal I, extending scalars from A to R. So this is an object of the derived category of R, which is automatically P complete. And an example, or the sort of defining property of this construction, is that if you apply it to the abelian sheaf represented by some U, then what you get is just the compactly supported perfectoidization of U. A warning that this passing from prism to prism bar is nice because the ring is a little smaller, but the price that you pay is that you no longer have a Frobenius automorphism of this complex. But nevertheless, for the rest of this lecture, I want to focus mostly on this RH prism bar, just because it will make all the statements a little easier to make. But everything I'm going to say is also going to have an analog for this construction that produces A modules instead. Okay, so I want to give you an idea of what this looks like. So let's start with a situation that we already understand. So let R be a perfect FP algebra. So then it's also a perfectoid ring. And let X be its spectrum. So what is this functor RH prism doing in this case? It's Well, you take an abelian sheaf on X, you reduce it mod P to make it into a sheaf of FP vector spaces, and then you just apply the Riemann-Hilbert functor of the preceding lecture. And this is essentially true by construction. The construction that I sketched for you, it was motivated by wanting to agree with the construction that we already had when we were actually in characteristic P. I guess one difference is that now we're working at the level of derived categories rather than the level of abelian categories. So that's what RH prism bar looks like. On the other hand, this RH prism you can think of as an upgrade of the Riemann-Hilbert functor of the previous lecture. So RH prism, when you apply it to p torsion sheaves, you get you recover the construction of the previous lecture, but you can also apply it to sheaves which are not p torsion, and it produces answers that are Frobenius modules, now not over R, but over the ring A, which in this case is just the ring of Witt vectors of R. Okay, so that's the characteristic P case. What about the more general case? So let R be an arbitrary perfectoid ring, let X be its spectrum. Well, you can break X up into two pieces. There's an open subscheme, which I'll call the generic fiber, which is the locus where P is invertible. And there's a closed subscheme that I'll denote by Y, referred to as the special fiber, which is the locus where P vanishes. And in this situation, every abelian sheaf on X fits into a canonical exact sequence. It has a subsheaf, which is supported on U, and a quotient sheaf, which is supported on Y. And there's a similar statement at the level of derived categories. Complex of sheaves sits in a canonical triangle. So if you want to understand what this RH prism bar is doing, you should ask, what does it do to things supported on U, and what does it do to things supported on Y? So let me first talk about Y, where we've essentially already given the answer. So let Y be the special fiber of X. You have a closed embedding of Y into X. And then RH prism bar, if you have something that comes from the special fiber, what you do is just take that sheaf on the special fiber, reduce it mod P to get a p torsion sheaf, and apply the Riemann-Hilbert functor of the preceding lecture. So that would be a Frobenius module over the ring R mod P. And in particular, it's a module over R. And the proof is just, it reduces formally to the case where R is itself of characteristic P, where it's what I said in a previous slide. There's no harm for sheaves that are supported on the special fiber of replacing R by its quotient, by the nil radical of P. So we're going to be interested mainly in what it does on the generic fiber. And I want to, before describing that, I want to go into a brief digression about the almost category. So let's say R is a perfectoid ring, then you can always extract from it a perfect FP algebra by dividing out by P and anything such that some power of it is divisible by P, dividing out by the nil radical of the ideal P. Definition, we say that an R module is almost zero if it's annihilated by this nil radical. That's equivalent to saying that M has the structure of a K module. And we say that a complex is almost zero if each of its cohomology groups is almost zero. So the almost zero complexes form a full triangulated subcategory of D hat R, and you can form the Verdier quotient. You divide by the almost zero complexes and you get what's called the almost category of R. I'm going to denote that by D hat R with the decoration A. So what's the relevance of this to what I'm talking about? So let's R be a perfectoid ring and let X be its spectrum. Again, we have this decomposition into two pieces, and we're interested in studying this RH prism bar. It's a functor that goes from sheaves on X to the derived category of R. Well, I've already said something about what that does to sheaves that are pushed forward from Y. Right? It's computed by the Riemann-Hilbert functor of the previous lecture. That would be something that produces Frobenius modules over this ring K. And then you can view those as R modules by restriction of scalars. Now, this almost category of the previous slide is what you get by taking d hat of R and forming the Verdier quotient by the image of this subcategory. And you can also do that on the top line. If you take sheaves on X and divide out by the subcategory of sheaves that are supported on Y, what you get is the derived category of sheaves that live on the open set U. And so there's some arrow that completes this diagram. It's some construction which takes sheaves on the special fiber and lands in this almost category. And so what my goal for the rest of this lecture is to give you a sense of what this construction looks like. So for this, I'm going to need a little bit of rigid analytic geometry. So let R be a perfectoid ring and let X be its spectrum viewed as a scheme. But another thing that you can do is to take its adic spectrum, to take the aphanoid perfectoid space given by SPA of R joint 1 over P, comma, whatever the appropriate ring is over there. So a friend of mine once made an observation, which I thought was kind of interesting. He said that you can tell how mathematicians feel about things by the font that they use. So, if someone says, let G be a group, 99% chance G is in a Roman font, because we feel like we understand what it means to have a group. But the more exotic an object seems, the more exotic the font gets. So, X here is a Roman X because I feel comfortable with schemes, but you can tell by the fact that this is a calligraphic letter that I'm a tiny bit afraid of it. But never mind. X is an aphanoid perfectoid space. So on X, I want to look at the sheaf of integral functions, OX plus. And now there's a map from this aphanoid perfectoid space to this scheme. Or more precisely, there's a map from the étal site of X to the étal site of the scheme. And it actually factors through this open subset where P doesn't vanish. I'll denote that map by mu. And with this notation in place, I can just give you a formula for what this RH is doing at the level of the almost category. So if you have a sheaf which is supported on U, you extend it by 0 to X and then apply this RH prism bar. What do you get? Well, it can be computed using the theory of perfectoid spaces. Namely, you take your sheaf, you restrict it to the étal site of X, and you tensor it with this sheaf OX plus, and you take the global sections of the result. Let me just add a caveat. What I said is true on the nose when F is a bounded complex of sheaves. If F is unbounded, I should be a little bit, to make this statement true, one needs to adopt the right conventions for dealing with unbounded complexes. And so I've implicitly chosen some conventions in this statement and in the statements that follow that are going to make the statements true. And I'm going to leave those conventions implicit. Okay, so I want to just go back a minute to what we said in the previous lecture. So let's be in the setting where R is an FP algebra, X is its spectrum, and then we defined this Riemann-Hilbert construction, which took P torsion étal sheaves on X to Frobenius modules. And I gave you two formulas for it. Right? First, I gave you an easy formula when F is a local system. What you were supposed to do is just take F, tensor it with the structure sheaf of X, and take its global sections. And the general formula was that this Riemann-Hilbert functor was given by some X group on some big étal site. So what I was saying on the previous slide is that this RH prism bar, it's computed by a formula that looks like A. The difference is that it's now not on the étal site of X, it's on the étal site of this perfectoid space. And you might ask, why are you allowed to do that now? So, so what's the problem in the setting of last week's lecture with trying to take formula A as the definition in general. So if you take your étale sheaf F and tensor it with OX, you'll get a sheaf of OX modules. Now, if F is a local system, that will be a quasi-coherent sheaf of OX modules. And therefore, replacing that sheaf by its global sections is not going to lose any information. But if F is not a local system, then this sheaf will typically not be quasi-coherent. And it's not something that you expect to be able to recover from its global sections. In fact, a typical, you might expect there to be no global sections at all. So that's why you want to avoid formula A. And what I want to say is that in this rigid analytic situation, this problem doesn't arise. So let me explain this again by brief digression. Let me review something about schemes. So let R be a commutative ring and X the affine scheme spec R. So then there's a construction. Given any R module M, you can make a quasi-coherent sheaf on X. You just take M and tensor it over R with the structure sheaf. And that's a construction you can do not just for R modules, but also for complexes of R modules. Given a complex of R modules, you can tensor it with OX, and you get something that lives in the derived category of OX modules. And this construction actually gives you a fully faithful functor of derived categories. The derived category of the ring R embeds into the derived category of all OX modules. And the essential image is the quasi-coherent derived category. And a particular consequence of this, or well, more or less a restatement of this, is that if you have any complex of R modules M, you can recover it from M tilde by taking the hypercohomology with coefficients in R tilde, taking R gamma. Now, in the world of perfectoid spaces, something very similar happens. So now let R be a perfectoid ring, X is the associated affinoid perfectoid space. And to every p-complete complex of R modules now, you can associate something that I'll call again M tilde, you get by taking M and tensoring it over R with OX plus. So this lives in the derived category of OX plus modules on the étale side of X. And there are hats everywhere to indicate that I've p-completed. And this construction is actually fully faithful again once you pass to pass to almost categories. And the situation is even better than that, because the essential image of this functor is actually something that you don't have to invent a new name for, because it already has a name. The essential image is sheaves which are p-completely overconvergent, meaning that they're overconvergent when you reduce them modulo p. And the essential content of the full faithfulness is that given M, a p-complete complex of R modules, you can recover it from M tilde, at least in the almost category. Namely, there's a natural map from M to the hypercohomology of M tilde, and that's an almost isomorphism. So when M is equal to R, this is a theorem of Peter Scholze, and it's one of the first things that you check to get the theory of perfectoid spaces up and running. And in the general case, it's closely related to some statements that appear in the thesis of Lucas Mann. Okay, so what does this buy you? So I want to use this to give another construction. So let R be a perfectoid ring, let X be this affinoid perfectoid space. And now suppose that I give you a sheaf that now lives on that perfectoid space. I'll say again, it's p completely overconvergent if it's overconvergent after reducing it mod p. And if that's the case, then the analogous property still holds after you tensor it with this sheaf OX plus. So that's a overconvergent OX plus module. And therefore, if you believe the theorem of the previous slide, then you believe that that's quasi-coherent. You believe that it's something that you can write as OX plus tensored over R with some R module. And moreover, that R module is uniquely determined as an object of the almost category. So I'm going to denote that by RH prism bar of F with an A for almost. And this construction gives you a functor from overconvergent sheaves on the perfectoid space to this almost category, which explicitly, if you want to, you can recover that by taking F, tensoring it with OX plus, and taking hypercohomology again. Okay, so I introduced this because that's what my previous functor is doing at the level of the almost category. I guess I already made this statement, but now let me say it again. So R is a perfectoid ring, X is the associated affinoid perfectoid space. And there's a commutative diagram where on the left here, we have this Riemann-Hilbert Functor RH prism bar that I described at the beginning of the lecture. It takes étale sheaves on the scheme X and produces complexes of R modules. And what I'm saying is that if you're interested in where they land in the almost category of R modules, you can compute that differently. You can compute that first by restricting to the generic fiber. That's what we said earlier. But you can further restrict to the generic fiber viewed as an adic space, this affinoid perfectoid space X étale. And then what you're supposed to do is this construction of tensoring with OX plus and taking global sections, what I'm denoting by RH prism bar almost. Okay, so that is a story about RH prism bar. But as I mentioned earlier, there's an analogous story if you don't want to work modulo the ideal I. So if R is a perfectoid ring written as A mod I, there's also this RH prism, which takes étale sheaves on the scheme X to the derived category of A modules. And that has an almost counterpart, which factors through this category of overconvergent sheaves on the adic space. Now, why might you be interested in this more refined construction? Well, if you want to know how much information that the Riemann-Hilbert functor is losing, this more refined version is not losing any information. That as long as you remember that it takes values not just in A modules, but in Frobenius modules over A. So this RH prism gives you a fully faithful, well, sorry, it's fully faithful once you p-complete the left-hand side. I told you earlier that the Riemann-Hilbert functor annihilates any sheaf on which p acts invertibly, and the same is true for this construction. But when you restrict either to p-complete objects or p-torsion objects, this functor is fully faithful. And the proof of that is relatively formal once you, if you give yourself the entire apparatus of the theory of perfectoid spaces. That is, you reduce it to a question on the tilt, and on the tilt, it's just the exactness of the Artin-Schreier sequence. So what does that mean about this original Riemann-Hilbert functor RH prism? I mean, I started by saying that I wanted to generalize a construction that we knew in characteristic P that was a fully faithful functor. So this RH prism, I think, it is not fully faithful if you think of the domain as sheaves on the scheme. But the reason is because this mu upper star is not necessarily fully faithful, that you can lose some information by passing from the world of schemes to the world of adic spaces. All right, I think that's all I have. Thank you very much.